Okay, good day. This is AP Calculus. I am Mr. McColley, and this is our presentation for section 6.1. It's going to be probably an in-depth one since there's a lot of new terminology, so let's get right at it. Today we're going to talk about using initial conditions to find the particular solutions of differential equations. And we're going to talk about using slope fields to approximate solutions of differential equations. And good news, Euler's method is not on the AP Calculus test, so we're not going to do that. So first thing, what is a differential equation? Well, we've spent a lot of time the first 5 chapters of this talking about how to do derivatives, how to do integrals. And we spent a lot of time talking about the ins and outs. What do I do in this case? What do I do in that case? And we've kind of gotten away, at least in the last 3 chapters, about what is a differential? What is a derivative? How do these things relate? Obviously, the integral is the reverse operation of the derivative. But what are they? Well, a derivative at its core is a rate of change. And a rate of change can be anything. And that's really what calculus is. It's the study of the change that's going around us in our everyday world. And so a derivative can represent just about anything that's changing. We've used it a lot. Speed is a derivative. The change in velocity or change in distance over the change in time. And that's just a real simple one. We can also talk about it a formal definition. A differential equation involves x, y, and the derivative of y. And in physics, something that you've seen probably quite often is force equals mass times acceleration. This is a simple example of a differential equation because it relates mass and force through a differential. It's acceleration. And since acceleration is the first derivative of the velocity equation, A is the differential dv over dt. The general solution, though, and this is going to be something that they're going to ask for quite a bit. So it's important that you understand what a general solution is versus a particular solution, which is what we'll get into in the next page. But one method for solving differential equations is by integrating. And this is just this, like, again, low level, simplest thing, so you get your mind around it. You'll get into the details later. But we're going to integrate most times to get the general solution of a differential equation. And we learned in chapter 5 that when you integrate, you must add a constant. And we don't know what that constant is. And so with that unknown constant in that solution, it's called the general solution. Then, when you're given an additional piece of information, namely some sort of initial condition, we can solve for that unknown constant. We have a particular solution. So a general solution is going to have some unknown constant in it, and the particular solution is just going to be a regular equation with all of the coefficients known. And as an example about this, trying real low level, keeping it easy to start with. If I give you an example, this is a differential equation. The derivative of y over the derivative of dy over dx is equal to 3. Find the equation of a line given this information. Well, we know something about a line. We know that the slope of a line is a constant. And we can essentially say that the derivative of any line is its slope. All right. So when I look at this thing and I'm kind of getting a little bit ahead. I'm kind of trying to mix what's coming and today's stuff together. This isn't really in the book, but one way to solve a differential equation is by splitting the variables, separating the variables. So if I start with this equation and I say dy over dx is equal to 3, then dy equals 3 dx. All right. And what we're going to do is we're going to integrate both sides of that equation. And so the derivative of 1 dy is just y. And the derivative, I said it backwards, the integral of 1 dy is just y, and the integral of 3 dx is just 3x plus some constant c. Yes, there should be a constant over here, but what mathematicians usually do is they usually say, well, I moved it over to there and combined it with this constant. It's just, that's the constant right there, okay? And this thing right here, this is our general solution. But I don't know what that is. If I look at an equation here, or I look at my graphing calculator, 3x plus 2, 3x minus 7, or minus 5, and I hit graph on all those, I've got 3 different lines. I don't know which one it is. In fact, I could have a line that has any y-intercept, as long as it has a slope of 3. Well, this initial point, or this initial information, tells me that when x equals 0, y equals -2, well, that's an x value and a y value, and I can figure it out. And from Algebra 1, we remember that anytime you cross the x, or anytime you have a x equal to 0, you're crossing the y axis. So this thing is not only a initial condition, but it's also a y-intercept. So we can just take that -2, plug it in for c, and say y equals 3x minus 2. And this is our particular solution. All right. See, hopefully we see the difference there. Okay. The second goal was to talk about slope fields a little bit. And then we've looked at slope fields, but we've never really formally defined them. Excuse me, drink of water. Where was I? So we've seen slope fields, but we've never particularly defined them, and we've also not drawn any. And we're not going to fill this whole thing with a slope field. We're just going to do a couple points, and that's probably all I'll ever ask you to do. But if you look through your book, you'll see slope fields with lots of the line segments. But slope field can be used to find the particular solution of a difficult differential equation. A slope field consists of line segments at specified points on a graph that show the slope of the function at those points. So here is our differential equation, our derivative, and so what we're essentially going to do is we're going to make a field, or going to pick out some points, we're going to make a field of line segments that are the slope at those points. So just picking some points at random: 0, 0, 1, 0, 0, 1, 1, 1, and let's do -1, -1. So when I plug in 0, 0 into this derivative equation, I get 0. When I plug in 1, 0 into this function, I get 2. When I plug in 0, 1 into this function, I get 1. When I plug in 1, 1 to this function, I get 2 plus 1 is 3. And then when I plug in 1, -1, I get -2 minus 1 is -3. So what I'm going to do is going to take these derivatives and I'm going to draw just a line segment that has that slope. So at the point 0, 0, I have a slope of 0 for this differential equation. So you draw a line segment that has a slope of 0. At 1, 0, I have a line segment that's I'm going to try and draw with a slope of 2. So if you look at it, I have that. If I went from 1, 0 to 2, 2, that line would have a slope of 2. So I'm just guesstimating here. This isn't going to be real exact. As long as you're close, I'm going to give you credit. Okay, and then so at 0, 1, I have a slope of 1, and 1, that's a slope of 1. So I'm just going to draw one little line segment that tries to have that. At 1, 1, I have a slope of 3. So the only thing I'm going to try and do is try it a little steeper than this one. So 1, 1, trying to draw in a slope of 3. And then my last one that I have on my table, -1, -1, has a slope of -3. So I'm trying to draw it that same steepness, except negatively. If you go up 3, that's pretty close enough for government work. Now I only have 5 of the points in the slope field, and obviously slope field pretty much does every vertex, but That's going to be good enough for at least this point. Once again, Euler's method is not covered in the AP Calculus AB test, so we are going to skip it. We're going to go right into some simple examples. Look, first, we're going to start with page 411, number 4, and you'll see that it asks you to verify the solution of the differential equation. So what they're giving you is they're giving you the solution. And they say in this particular instance for 4, they say y squared minus, let's see here, 2 ln y is equal to x squared. I think that looks right. Okay, and they want us to show that it is the solution of the differential equation and they say dy over dx is equal to xy over y squared minus 1. xy over y squared minus 1. All right, so I can find the general solution of a given differential equation by differentiating or integrating, so I can show that the solution is, or I can show that an equation is a solution of a differential equation by doing the derivative of that function. So I'm going to take the derivative of this function, dy over dx. So the derivative of y squared, because we're deriving with respect to y, because that's what we need. So I'm going to get dy over dx is going to equal, let's see here, it's going to be 2y, and then I have to, I'm deriving with respect to x, not y, times the derivative of y with respect to x, minus 1 over y times dy over dx, and then that's going to equal 2x to the first. Okay, so each term here has a, let's see, each term here has a factor of 2. So let's just cancel those out. We'll get rid of those right off the bat. And then we'll factor out a dy over dx from both terms. So I got dy over dx is going to leave me, let's see here, y minus 1 over y equals just x. Okay, now we could derive we could divide this and that'll work, but before we do that, let's combine this into one fraction and then we can just flip and multiply, and that's, we're going to get there. I have a feeling. So this thing I have to multiply by y over y. So I got dy over dx is going to equal y squared over y minus 1 over y equal to x. And we can see real quickly dy over dx is equal to y squared minus 1 all over y equal to x, and we're going to divide both sides by this expression or multiply by the reciprocal. So dy over dx is going to equal x times the quantity, again reciprocal of this, y over y squared minus 1, which gives me my solution, xy over y squared minus 1, which is what we wanted because we just wanted to confirm that it was equal to that. Okay, moving on. Example, or talking about number 14. Now, the reason I picked number 14 is because it's determine whether the function is a solution to the differential equation y, and they put it parenthesis 4 minus 16y equals 0. And then they give us that the function y is equal to, in number 14, 2 sine x. Okay, and so this here is what I'm most concerned about. Y in parenthesis 4, this is the fourth derivative. We haven't seen that in a while, so I thought I'd go over that. So y prime is just going to be the derivative of sine x is cosine x. So I got 2, and then I've got cosine x. And again, there's no chain here, so just do the derivative of it. The second derivative of that is going to be 2 negative sine x, because the derivative of cosine is negative sine x. And then the third derivative, and I'm just going to bring my negative 2 up front, sine, actually, let's do it this way. We'll say that that thing is equal to -2 sine x. So the third derivative is equal to -2 cosine x. And then here it is, the fourth derivative is going to be -2 times negative cosine, negative sine x. There we go. And that gives us 2 sine x, which is the original one. And so the question asks us, is it a solution to this equation? Well, if I plug in 2 sine x minus 16 times y, which was, again, 2 sine x, I get 2 minus, let's see, 16 times 2 is 32. Yeah, 32. 2 minus 32 is -30 sine x. And since that's not equal to 0, this is not a solution. All right, moving on. Number 22. In number 22, it says, determine whether the function is a solution of the differential equation. And they give it to us like this: x, y prime, minus 2y equals, let's see here, x to the third e to the x. Now, we are given as our equation in number 22, y equals x to the third. Okay, so we want to see if that's a solution. So I need y prime. So y prime is going to be 3x squared. So essentially, all I'm going to do is I'm going to plug in what I know on the left-hand side and see if it equals the right. Pretty simple. So x times, well, y prime is 3x squared, and then minus, just make it look a little neater, x times x to the, one more time, 3x squared, because that's what y prime is, minus 2 times x to the third. Well, when I multiply this out, I get 3x squared minus, again, I am really good at calculus, but really terrible at arithmetic. X times x squared is x to the third, minus 2x to the third, which is just x to the third, which is definitely not equal to x to the third e to the x. So this is not a solution. All right, moving on. Number 36 on the next page. It says, verify that the general solution satisfies the differential equation, then find the particular solution. So they're saying in number 36 that 3x squared plus 2y squared equals c is the general solution to the differential equation, and they give it to you in the second one, 3x plus 2y prime equal to 0. So we want to show that this general solution is this equation is the general solution to this differential equation, which isn't too bad. All we're going to do is differentiate. So the derivative of 3x squared with respect to x is going to be 6x. The derivative of 2y squared with respect to x is going to be 4y times dy over dx, and the derivative of any constant is going to be 0. Now, notice all of these two terms have a factor of 2. So if I divide everything by 2, I have not changed that particular problem. So I have 3x plus 2y, and then dy over dx can be rewritten as y prime equal to 0. Lo and behold, check that out. There is our differential equation, and then they want us to find the particular solution. Well, the particular solution, I take my 3x squared plus 2y squared equals c, this original one. These two are equal. I go back to my original function, and I say, all right, I have been given y equals 3 when x equals 1. So I plug those values in. I've got 3 times 1 squared plus 2 times 3 equals whatever constant. So 1 squared is 1 times 3 is 3 plus 6 is 9. That equals c. So my particular solution is just the general solution with the constant filled in. So 3x squared plus 2y squared equals 9. And that is our particular solution. All right, last one, number 44. And I'll do more examples in class during our class time if you need them. All right, number 44, it says, use integration to solve the general solution of the given differential equation. So they say dy over dx is equal to e to the x over 4 plus e to the x. So again, we're going to, and I'm using a term for the next section, I'm going to separate my variables. I'm going to dy equals e to the x over 4 plus e to the x, dy over, excuse me, it's just dx. And we are going to integrate both sides. Now, the derivative of 1 dy is just y. This one, though, is a little bit more complex. But I do have, excuse me, a 4 plus e to the x on the bottom of a fraction. And so this is, it seems to be a little bit more complex. So I'm going to let my u equal 4 plus e to the x, and then du is going to equal e to the x dx. Because the derivative of 4 is 0, derivative of e to the x is e to the x. And so I have this. So this is in the form 1 over integral 1 over 1 of u du is this ln u plus some constant c. So I'm just going to rewrite this thing as the ln of 4 plus e to the x plus some constant c. And that is my general solution. All right, that is it. And I know I went a little long, but here is what I like. Today, I would like for you to, when you finish this, email me at gmail.com, and in the subject line, just put diff EQ and DG, diff EQ, and that, put it in the subject line, and that's it. Send it to me at there, and then I will know that you have seen this. Thank you for your attention, and have a good one.